So I'm going to introduce now our second to youngest, newest program manager. Oh, is it break? Oh, Martine's next. Okay. Oh, good, she's here.
I'll take that job.
That's great.
I want that job.
No, Martine is here. Good, I'm grateful. So is Mike Callahan here? Is Mike? So Mike, could you come up? So Michael Callahan was a DARPA program manager, good friend of mine who joined the agency the same time I did. He has since moved on. Mike is a professor at Harvard University, infectious disease doctor, and I've asked him to introduce Martine to the audience.
Even DARPA needs a 7-year-old child to help us with technology. So my iPhone met its demise in a Starbucks cup of hot coffee today, and that's where my notes are for Martine. But I know enough about Martine, who is my boss, and I'm happy to tell you is the first ever conflict of interest I've ever had as an ex-Fed. As Martine gave me the opportunity to develop that conflict of interest when I joined her company, United Therapeutics. There's a bio in your package, and Martine is very easy to learn about in terms of her lineage and how she got to where she is, but I'm going to reconcile it or redact it just for the group here and focus on her innovation. If you'll allow me just about 15 to 20 seconds on this. So in DARPA, it's about enablement. The program managers come in with a vision. They're supported by ACETAs, which are our extraordinary fuel cell that helps us to get the work done. So the combination of that partnership is broken without your part of the partnership. And that is the performer community. We learn from the performer community without a doubt. It's very helpful to us then to see these occasional bright spots in the wilderness that happened outside of DARPA's fold. In DARPA, you get an unfair advantage. It goes far beyond the support that you get. You're given an unfair access that the competition doesn't have to technologies that lever your own expertise, your own passion, your own energy. So when a group does this outside of DARPA without that access, without that global intellect brought to bear and put on a laser focus through the contracts and the deliverables, it's really extraordinary. In my search globally, and I do venture capital in China, I sit on the Singapore National Academy of Science in terms of redirecting Singapore funds. I work in the Panama Canal Authority for Maritime Security. I meet a lot of very interesting multidisciplinary people, but no one is a better example than Martine. The journey that I'll just summarize with her, which she will share in her own story, is one about really transhumanists. It meets very much the focus of the biology is technology, but she embodies this with her actual experience. It's not just Sirius Radio. It's not just her other telecommunications programs. It's not the co-joined work that she did with the UN for the human genome and human rights. So this ethicist, aviator, supreme technophile has done it again and again in the private sector. And with her life partner, Bina, has created a vision that has inspired about, I don't know, just shy of 900 people. We're called the Unitharians at United Therapeutics. And we're asked to do the right thing at the right time, the right way, all the time. And this is a great decree for which we can also guide our own management of the programmatic vision. So with that, what I'd like to do is turn it over to Martine, my boss, and my conflict of interest. Thank you so much. Mark.
I think I got my own thing here. Thanks very much, Mike. It's absolutely a great pleasure for me to be able to work together with Mike, creating new futures. Although I really would like that program manager job. I mean, you sold that position so well, and I couldn't think of a better job. So if you have a spare one, I'm available. Okay, thank you, thank you. I can multiplex, I can do, yeah. I'm really excited to be here. When Alicia first invited me, I said I am a total dyed-in-the-wool fan of DARPA, always have been. So to be here to speak today is a great honor for me. It's also a real pleasure to be able to speak on the topic of biology as technology, which I would say is probably as close to a religion as I could claim for anything for myself. So it's the perfect topic for me. I thought in preparing for this talk, I thought a little bit about the meaning of the words biology and technology. I'm very much in the school of sort of the Elon Musk school of do whatever doesn't violate the laws of physics. So when I think about life, I think about Erwin Schrödinger and his definition of what is life, which was more of a physicist's approach to it, of something that increases negative entropy by streaming order into itself. And technology, really, as I thought about it in preparing for this talk, does very much the same thing. The only real difference is that technology imposes the element of intent. Intent means lots of different things to different people, but for the purposes of I think, universal applicability, intent involves some level of simulation. You're running something inside a processor, which for us is our mind. There's going to be some selection out of all of those alternative possibilities, and then going ahead and satisfying or trying to satisfy one of the alternative realities that you've run in your head. So biology, in my view, used with intent, is technology. And that's a broad definition, but I think it works pretty well everywhere. So here's just a quick little graphical version of the same thing. It's all credit goes to Schrödinger. You've got this environment that we're immersed in, and as the living creature, which could also be technology, goes ahead and streams order from that environment, thereby creating negative entropy upon itself. You have either biology or plus intent technology, and then amongst us humans, you have a little bit of both. Sometimes there's technology, sometimes there's just plain biology. Now, in my particular case, I started by trying to stream order in the area of satellite communications. My first projects were one to build a GPS receiver that cost under $100 and could be used by Joe Sixpack to fish bass fish in ponds in the South. Again, as we were told, people said that's absolutely impossible, no way, no how. Of course, now costs have fallen a couple orders of magnitude, even below that. But that Humminbird GPS was a great success, and a lot of fishermen happily knew just where to go in their big bass ponds to find what they wanted to do. The next project was to have a handheld transceiver that could go ahead and communicate tweets back and forth with geostationary satellites. This is a GeoStar system, also used for navigation and control. That too was something that people thought was impossible, but it really amounted to was just what was described at the beginning, is going ahead, specifying what you needed. In this case, one of our customers was from Fort Meade, so it was necessary for the device to actually be able to handle all sorts of unusual threats which worked against its consumer acceptability. But nevertheless, we streamed order from the satellite communications industry, from the microelectronics industry, from the regulatory authorities, and ended up with another cool consumer product. So, but in each case, what really happened is it started with a dream and a passion that there is in my mind, and in all of your minds. There's a simulation going on of all these different alternative realities, like maybe there could be a GPS receiver I could fit in the palm of my hand. Or maybe I can go ahead and track vehicles and people and aircraft and exchange messages anywhere on the surface of the Earth. And then going ahead and going from that simulation and all the different ways to meet it to selecting one pathway that seems you can actually get it done in like 2 years rather than 2 decades, because that's no fun to work on something forever. And then finally going ahead and taking the implementation steps of digesting the order that's in the external environment to create a more cool order, a better order, a faster, more efficient, more awesome order in a new environment. So that's technology as biology. Another example that I want to point out is that the crucial role of using biology as technology goes beyond the things that we'll probably hear a lot about today, beyond the genes and codons. And the human mind, as we just saw a brilliant presentation of, is a magnificent piece of biology. So the next telecom product that I created was a satellite radio system that could broadcast hundreds of channels of commercial-free CD quality music throughout the United States. And again, it started off with a simulation. Okay, there's 100 different ways to do it. I'm going to select down to these 3 ways I'm going to implement, and we ended up with this beautiful, totally functioning Sirius XM satellite radio system. The only problem was that people were not buying this system in the numbers necessary to pay for the $100 million launch costs of satellites and the multi-$100 million cost of building satellites. So we needed to co-opt biology as a technological adjuvant to make it happen. And there was a guy who was on an AM and FM radio when he was not being banned or fined by the Federal Communications Commission. And this individual's personal magic was what turned Sirius XM from a would-be technological bankruptcy to a huge success. So I have this little audio clip that you could see just how much this individual loves this system, and approximately a third of all the people who subscribe to Sirius XM subscribe because of this guy. In fact, I have had more people thank me for bringing Howard Stern into their little hamlet from the Canadian border of New Hampshire down to a small place in Nebraska, then I've had people thank me for our medicine saving their children from pulmonary disease and cancer. It's crazy. Oops, I'm sorry. Audio, please.
This is an exciting time. I mean, you invented this whole deal, and here we are. We're enjoying it. And as a broadcaster, I said this to you in the hall, and I'll say it to you on the air. I thank you. If you hadn't invented this medium, I mean, the fact that I'm getting to look at this is like me meeting Marconi. If you hadn't invented this medium, I would have been out of the radio business.
I liked it better when you said this is like meeting Martine Luther Queen.
Oh, that's true. That's a whole other thing. But it's true.
Did you say that?
I did.
You're a witty guy.
But I got to tell you something. I am so grateful that you invented this medium. I mean, I am flourishing here and also able to be part of something from the ground up. But I mean, this has got to be nuts. This was a dream in your head, and now you're seeing it all come together. What is your...
So the point there is that when we're thinking about biology as technology, the brain is like, I'm not going to be able to say it's the coolest part of biology because what goes on in every single cell is awesome beyond comprehension. But, the brain is a crucial part of biology, and we've got to co-opt brains to make a lot of our technology truly happen. And that's what the story of Sirius XM was. So the next thing that happened in my life is as I was doing Sirius XM, my youngest daughter had a failure of biology in which her system, her DNA was no longer coding for enough of an absolutely crucial molecule that's necessary to keep blood vessels open and free from occlusion. So it was a failure of biology. Here what we did is we went ahead and said, okay, we understand what the failure is. Let's take that biology, let's take that molecule. Nature developed this molecule over hundreds of millions of years of trial and error. Even mice without this molecule, prostacyclin, are non-viable. We can replicate that molecule. Oh, but this molecule is so necessary and used so continuously in the blood vessels that it only has a 30-second half-life. How can you give somebody a medicine that has only a 30-second half-life? Well, the way to do is to stream it continuously, 24 hours a day, 365 days a year for a person's entire life, and make it so easy and seamless that the individual can go rollerblading, snowboarding, live a real life. Nobody had ever done this before. Before we got the FDA to approve this technology, there had been no other medicine that was streamed 24 hours a day, 365 days a year, subcutaneously for a person's entire life. We did it. We got it approved. My daughter is now 31 years old, happy and healthy, as are thousands of other young women and men with this disease. So failure of biology can be fixed with biology, the molecule, as technology. Intention, I mentioned like the key to this whole biology as technology thing is that technology is just biology with intent. Intent is Darwinian variation and selection at hyperspeed. So just because technology does not look like these biology textbooks, anthropology textbooks of worms to fish, to mammals, to reptiles, to mammals, to us, doesn't mean that it's not happening. All around us, we humans are the most important environment for technology, and we can affect that environment with our own intention. Intention is how we mutate different products. As we were told, fail fast, fail often. That's Darwinian variation and selection occurring at hyperspeed in the human environment. When people fret and worry about things like the Luke arm and robots and whatnot, and they watch all the dystopian Hollywood movies and believe that stuff, I tell them, it's just fantasy, really, because there is no market for a crazy robot. We are the environment, okay? We are the Darwinian environment in which all this technology has to operate. We all have dogs because they're nice. I love dogs. I have 4 dogs. What's going to happen to the dog that bites my arm? It's going to be put down. I mean, that's just the way it is. Okay, so there's another end-stage organ failure that cries out for technological biology. About 1 million Americans a year die of end-stage organ failure. And this fact is pretty much kept hidden from us by the very much smaller list of people who are on the organ transplant list. The organ transplant list is a highly, highly managed list. It's managed to be so small so that people who are on the list have a reasonable chance, something like a 50-50 chance, of actually getting an organ transplant from a human donor within 1, 2, maybe 3 years. So to do that, vast numbers of people who need an organ because of end-stage organ disease are just never allowed on the list in the first place with so-called objective medical and sometimes socioeconomic criteria. Now, of all of these hundreds of thousands and actually 1 million people who die of end-stage organ disease, the number of people who get them are somewhere on the order of just a few tens of thousands of people a year. So we are talking about something on the order of 1% of all the people who need an organ actually will ever be able to get one. Now, the reason why so few people get one is that even though quite a number of people die every year, in the US, upwards of 2 million people a year die, 99% of those people die in a way that their organs are ischemic or without blood flow by the time anybody could get to them and would rapidly degrade. So as a result of that, there's only about 1% of all US deaths that are so-called brain-dead donors or non-ischemic donors, and there's a possibility of harvesting their organs for transplantation. And that 1% of 2 million, that's 20,000. And then when you count for the heart, couple lungs, couple kidneys, you get a pretty good match of the low tens of thousands of people who actually receive an organ transplant, still far fewer than the number of people who need it. Now, remarkably, of those 1% of 1%, of that very small number of brain-dead donors who donate their organs, there is a differential situation between the abdominal organs and the thoracic organs. The thoracic organs, the chest and the heart, more than half of them are actually thrown away, never used. And with regard to the abdominal organs, the kidneys, about 80% of those from the brain-dead donors, which are only 1% of all the possible donors, are used. So as a pulmonary disease company, we were really concerned with, oh my goodness, half of Americans are kind enough to agree to donate their organs, but doubling the number of people who donate the organs is really not going to solve this problem, because most of all those people, 99% of those half of Americans who are so kind to donate their organs are going to end up dying in situations when their organs are not even up for discussion. They'll end up dying of cardiac death, infectious disease, cancer, something other than being a brain-dead donor. So doubling the number of people donating is not going to solve the problem. Then, among those 1% of half the Americans who kindly donated their organs that are brain dead, then I find out that the transplant centers are taking 80% of those lungs, 80% of that scarce little 1%, and tossing them in biowaste. And they're not doing that because they're bad or evil or cruel people. They're great people. They're transplant surgeons. They're lifesavers. They're doing that because they have a patient who's on death's door. Otherwise, they wouldn't be at the top of the lung transplant list. And that patient who's at death's door this lung transplant is going to be the mother of all traumatic surgeries for that individual, or heart transplant. And the surgeon doesn't want to put something in there that's anything short of pristine. Anything else is going to kill the patient. And by the way, if you end up killing more than 20% of your patients, within a year or so, your whole center will be decertified for further funding for lung transplants. So all the factors make people very, very, very conservative. Well, after the abdominal organs are taken, after the kidneys are taken, there's no more vasopressin controlling blood pressure in the system. You've got to pump up the patient with drugs. The lungs burst. The heart is invaded by all kinds of cytotoxic chemicals coming from a dead brain. And within a couple hours, most of the time, the heart and lungs are no good anymore. So we got to thinking, well, there's B-52 bombers still flying with replacement parts that are being made, and they're being flown by pilots whose grandfathers built the original aircraft. So unlimited supply of parts for that. You go to all the antique car shows, okay? They got Mercedes being driven around that were actually manufactured in 1900, believe it or not. So why can't we have an unlimited supply of replacement organs for the body? Let's start by just going to the junkyard where we're throwing away 80% of what we need and just polishing it up and reclaiming it. And then let's develop a multi-year plan where we can get to the point of an unlimited supply of replacement organs is something which is taken as a health right, as much as we take for granted our vaccinations against pandemic diseases. So we have gone ahead and implemented this. We created a technology called Exvivo perfusion, where we take the organs out of the dying body, we put them into what is in essence a little artificial body, a technological body, one that is free of all of the toxic molecules being shed by the dead brain and all of the drugs which are being used to pump up blood pressure in a cadaver. So we put them in this very nice dome sort of structure, and we have solutions in the structure that are able to keep the organ happy, healthy, normothermic. Okay, so there's no more damage from going cold to warm, cold to warm. And I'll show you a little video of how this works. This is something that we're doing right now today.
A pre-EVLP biopsy is taken. The perfusion circuit is then primed, including drug addition. The heater cooler is connected to the heat exchanger. Then lungs are transferred to the procedure table by EVLP specialists. Pressure lines are zeroed, cannulas are connected up to the perfusion circuit, and air is purged from the lines. The perfusion pump is started, and with this step, the EVLP procedure clock starts. Perfusion continues over a 4 to 6 hour period with ongoing CMX documentation and assessment steps. These include bronchoscopy, X-rays, blood gas analysis, both on a regular and an as-needed basis. Throughout this period, the IT specialists in our command center facilitate visual and data communication with Toronto General Hospital and the transplant surgeons, keeping them informed on an at least hourly basis. At the 3 hour mark of perfusion, the collective team makes an initial assessment of the lungs. If the decision is made to go ahead with transplantation, the primary EVLP specialist contacts the transplant center to arrange transportation. After all the data is collected and the Toronto General Hospital surgeon and transplant surgeon agree on cessation of EVLP, the case is locked and a disposition email is automatically sent to the Toronto General Hospital surgeon, the transplant surgeon, and finally to the OPO, which confirms transfer of custody to the transplant center. Cooldown commences, and once the cold temperature set point is reached, cannulas are clamped and the lungs are disconnected and moved to the back table. The EVLP procedure clock is stopped. The lungs are then flushed with steam and stored in Perfidex. The EVLP specialists remove the cannulas, staple the trachea, and perform a post-EVLP.
So this is no like science fiction, or this is no I want this to happen, or I hope this can happen. This is something which is approved by the Canadian FDA already. So you heard the references to Toronto General Hospital. It's pending approval, no more, I would say, than 12 months from now in the United States. Already, nearly 1,000 lives have been saved with this technology. People do die on the lung transplant list every day. So people who otherwise would have died on the lung transplant list, instead there was an additional lung made available because we recovered it from trash, did 4 hours worth of Exvivo perfusion. And by the way, everything you saw in the video, all that nice high-def imagery, all of that is streamed to the surgeons, the transplant surgeons throughout the United States and Canada, to any device that they have, such as a smartphone, a laptop, an iPad. They could be, on the proverbial golf course. They can look on their droid. They could see everything going on. They could say, hey, I'm a little bit worried by the mucus down the bronchi. Can you go ahead and suction that out for me? They could watch while a bronchoscope is put down there and the mucus is suctioned out. They said, okay, that looks good enough. Start shipping it to me. So this technology is continuing to replicate. Our partner Transmedics has now accomplished over 150 hearts with this, in addition to several hundred lungs. Just last week, we announced an agreement with the Mayo Clinic in Jacksonville to build the second Exvivo organ perfusion center in Jacksonville. Each of these are capable of doing 2,000 lungs a year. So today, there's 2,000 lung transplants a year. By the way, by reference, 250,000 people die of end-stage lung disease, not even counting the people dying of lung cancer. Okay? So it's only all these transplants are only helping 1% of the people. But with just one center opening up, using just 1/4 of those 80% of lungs that are trashed, we can double the number of lung transplants. Now Mayo Rochester, Mayo Arizona, they each want one. In addition, we and our partners are selling the machines to hospitals throughout the country. So, I can very confidently feel that by the end of this decade, there will be something like 4 to 5 times as many lung and heart transplants going on as there are today, simply because of recovering brain-dead donor organs that are otherwise being thrown away. As a footnote to that, let me say that we have already successfully recovered cardiac death donor lungs. This is really amazing because we've recovered lungs that have been without blood flow for over an hour. And everybody, the dogma of this transplantation industry is that those organs are toast. They've had no blood flowing in them for over an hour. Nobody would even list them on the United Network for Organ Sharing. We said, send them to us. Send us your tired, mistreated, unwanted lungs. Worked on it for 4 hours. The transplant surgeon looked at it again through our high-speed network and said, whoa, that looks as good as a normal lung. Organs are amazing in terms of their ability to come back to life, especially if taken out of a toxic environment. And transplanted those lungs that, again, had just been shriveled up and nothing for over an hour. When he transplanted them, he said it was one of the best sets of lungs he'd ever seen. That patient, the recipient, is now discharged from the hospital, walking around perfectly good. By the way, the statistics, the survival statistics for these Exvivo lungs are that the 3-month, 6-month, 1-year survival, that's as far as it's been measured, is no different from if you transplanted a lung from somebody in one room directly to the person in the next room. So it's not like these people are getting any worse survival from all this. One last point before moving on here, which is, I think, makes it so exciting to be alive right here and now. There was and is an absolute dogma of transplantation science that says that after a certain number of hours, you cannot use an organ for transplantation. It varies by the organ, the kidney, the heart, the lung, but it's always a handful or a couple handfuls of organs. Like with the lung, after 10 hours of cold transport, okay, so the ischemia doesn't matter so much now because it was harvested, non-ischemic, and then quickly put into a cold preservation solution. And the dogma is that that cold preservation solution is good for 10 hours. After that, you're going to get reperfusion injury and other problems when you transplant. It's no good. What we do now, that was the dogma. Every transplantation doctor believed in that. Every center believed in it. Nobody would even try to transplant an organ that lasted longer than that. What we've done, what we discovered, and it's because we challenged the dogma, is you take a lung or a heart that's been in cold ischemia for 4, 6, 10 hours, ship it cold, put it on our Exvivo perfusion machine, it resets the clock. You saw how in the video, how we warmed up the organ and began reperfusing. It resets the clock. We discovered that you can be cold ischemic 10 hours, warm up for 4 hours in the perfusion machine, be well treated, okay, during that time with those techs, look at those lungs as their patients. Then you can cool it down. You saw in the video that then they pack it up to cool it down again and get another 10 hours of shipment time. Who knew? Okay, but that's what can happen now. Well, it's not enough to just use these brain-dead donor lungs because I think that will allow us to help some thousands of patients. But as mentioned, the need is 1 million patients, okay, not just thousands of patients. So we have 3 further steps in our Biology is Technology program here. And these are not just our steps. There are people throughout the country and the world who are working on these things. So EVLP, that's one I just talked about, being able to help thousands of people, doing it right now. Already about, I think we're up to about 750 people have already been successfully transplanted between the efforts of our machines, our affiliate company, Transmedics machines, and throughout the US, Canada, and Europe. Next up is Xeno. I was always blown away by the fact that my grandmother had her life saved with a pig's heart valve back in the late 60s, early 70s. And so I began to think, well, if the valve was, as I got older, I understood that the valve was devascularized. It was just a form, but it was the right form. Maybe if the valve fits, the heart might fit too, and maybe the lung and the kidney and the rest. Well, as it turns out that from porcine donors, all those different organs do fit. They fit nicely in terms of size and nicely in terms of function. Not so nicely in terms of how some of the molecules mesh together with regard to immunology and coagulopathy. So the idea began to percolate that maybe the way an artist, a sculptor, chisels off enough rock to reveal a beautiful sculpture from a hunk of stone, maybe we could chisel off enough genes on the porcine genome to go ahead and create a beautiful human-compatible organ from the pig. And it turned out that not too many genes had to be really chiseled off. In fact, the consensus is that somewhere between maybe 8 to 15 genes are the sum total of what needs to be modified in the pig genome in order to have the pig serve as a donor species for tolerable, that's the emphasis of the word, tolerable, possibly even with less or even no immunosuppressant organs to humans. We formed a joint venture with Synthetic Genomics, which I know is another recipient of DARPA BTO office support and is doing tremendously great things there. So those guys have now, together with them, We have sequenced the pig genome to a far greater level of resolution and clarity than anything in established database, identified ideal landing pads. We now have, using our genetically modified pigs with just 4 genes modified, we have the world's record for the pig heart surviving in the baboon model, which is what we used before people. That's 3 of them out over a year, 1 almost 2 years at NIH. And with regard to the lung, we have increased by already 1, now going to 2 orders of magnitude, the duration of time that the pig's lungs with 6 genetic modifications can provide life support in a baboon. So we are very much on the track here that by 2020, I'm confident that we'll be able to take the first human patient who has end-stage lung disease and provide them with a genetically modified lung, or if it's a heart disease, heart, and return that patient safely back to health. Once that's done, we will be able to ramp up using herds of homozygotic pigs for the genes of interest. I think we'll be able to ramp up to many tens of thousands of lives that we could save each year this way. What we're doing in parallel with this, again, biology is technology. In parallel, we are working with Harold Ott and the whole team at Mass Gen to go ahead and use the pig's lungs just as a scaffold. So we decellularize all the lungs all the cells off of the pig's lungs, and then we just have this beautiful collagen scaffold, recellularize those lungs with an iPS cell line, which is then redifferentiated into tens of millions of endothelial cells, proximal and distal epithelial cells, and mesenchymal cells. Amazingly enough, just those 4 different families of cells are all that's necessary to restore gas exchange capability in the small animal models that we've used already, and now we're ramping that up to a large animal model. So there will be pigs whose lungs are like, 99% pig genome, a little bit human genome, that will be tolerable in humans. That's the orange circle, 2020. And they'll be tolerable because the immunogenicity and the coagulopathy problems will have been genetically edited away. Plus, because these could be scheduled operations, we have time to induce tolerance so that there can be a level of immunochimerism in the human recipient. Then, at even larger numbers, we could just take the pig's lungs, strip them of their cells, and put human cells. So now these people who, the day they get transplanted, they're going to have the scaffold of a pig lung, but they're going to have all the cells are going to be human, okay? And so that's yet another step further, and I think with that we could take this up to perhaps 100,000 patients. And then ultimately, we're working with 3D systems to, in fact, actually print the scaffold, so we don't even need to use waste the time with the decellularization process of the pig scaffold, print the scaffold, and by this point in time, based on our learnings with iPS cells into the universal cell lines, we'll be able to do a specific iPS cell line for each individual person. So from any skin biopsy of them, we will iPS them back into a undifferentiated cell and then redifferentiate it along those endothelial, epithelial, mesenchymal cell lines. Believe it or not, you can grow up to the couple 100 million cells, and the cellularization of the entire organ, even a big organ like the lung, takes less than 8 weeks. The vast majority of the time, people who have end-stage lung disease and end-stage organ disease, they got a couple months to wait for their spare. But if they didn't, we would have the xeno lungs and the recovered lungs. So we will build new plants for this. Nothing like this has ever been done. This would be the mother of all biologics. But a big thing about technology is that when you got to build an aircraft, you got to build a big hangar. And when you got to build 100,000 lungs, you got to build a big designated pathogen-free plant to ensure those lungs can be done. Intention is not limited to human brains. I've talked about intention as being that thing which turns biology into technology. but our intention is not limited to human brains. This is, of course, a Kurzweil's chart showing that we're on track to be able to replicate human intelligence with cybernetics. A lot of people dispute the fact that we can ever have a human-like consciousness operating off of software, that there's something mystical about the brain, something from the realm of vitalism about the brain. But as Mike kindly alluded to my pilot credentials, you know, birds are just amazing at flying. They can do amazing feats, but so can planes, Mach 9. No bird can do that, you know, so, I mean, my point of view is just consciousness is to brains as flight is to birds. You know, there are different ways to accomplish the same thing. Then I also get some criticism, again, sort of like from this vitalist perspective, that, okay, you know, maybe you could make a brain smart enough to design a Mach 9 plane, but it's just going to be, it's not going to have intent, because intent comes from like the soul, from some deep place inside the brain. But I think, you know, we'll leave that question to the philosophers and the theosophers. But my view would be that souls emerge from minds, just like technology has emerged from biology. And I think that's really the theme of this conference, the technology emerging from biology. In fact, if you go all the way back to the RNA world, some 3.5 billion years ago, you always see that that which is emergent reshapes that from which it emerged. And there's always this interplay between the pedigree and the progeny. And it would only make sense because everything that came before constitutes the environment for what comes next. And if Darwin taught us anything, everything that comes next comes from the environment and is shaped by the environment. So there's really nothing magical here about the fact that technology emerges from biology and that minds emerge from computation. And then my last slide here is that synthetic biology, it's as old as, man making dogs from wolves, women making food from wild strains, and as new as how we're making organs. Here's an example of a super cool machine, the BioXP 3200. Splices genes together in under a day that used to take 1, 2, or 3 months, and including doing Gibson binding techniques, which would actually be impossible splicing techniques without this machine. So this in and of itself is accelerating to light speed the rate of biology becoming technology. This machine, I'd say, very much embodies as much as anything biology as technology. If DNA rearranging didn't exist, we wouldn't exist. That's kind of obvious. But what maybe is not quite so obvious to enough people is if we don't accelerate DNA editing, many of us 10 billion may not exist. We need to take charge of our biological universe and use all of the brilliant technology within biology to create a decent standard of living for the 10 billion people who can shortly be around. Mike kindly referred to my credentials as an ethicist as well. And people often say to me, oh, this is like unethical and blah, blah, blah. But I'm sorry, I shouldn't say it that way. But my friend Ralph Steadman drew me this. I actually drew like a very PowerPointy kind of chart, and then he said, no, let me really explain it better. And so this is my social acceptance of weirdness chart. This is, I think, all the take all those bioethics textbooks and it's just kind of one picture here. It tells you the same thing. There's pretty much a 45-degree line, which is as long as utility exceeds yuckiness, which is in the green portion of the curve, then there's social acceptance of weirdness. What once thought weird, like, test tube babies, like almost 1 out of every 50 babies today is a test tube baby. Not so weird, and certainly not if you're the one who wants the baby. Taking organs from dead people and slapping them into the chests of living people, whoa, but not so weird anymore. So the other cool thing is that, the utility doesn't really even have to be life-saving. It could simply be more convenient than disgusting. If you go ahead and you don't like your apples, turning all ugly and whatnot on your kitchen sink, and somebody's got some nice BioAs tech that can keep them nice and crisp, stuff like companies like Intrexon are doing, then it's not disgusting at all. In fact, it's very convenient. So the good thing about us people, probably why there's almost 10 billion of us, we're such good adapters, we adapt to this stuff very quickly. So in summary, intentional use of biology is what makes it technology. I've used it to spread satellite radio and help thousands manage their diseases. I'm using it to create an unlimited supply of transplantable organs and doing it now with no delay, step by step. If you can't do something in 10 years, then do 10 awesome things 1 year apart that are going to lead you to that thing in 10 years. So keep the awesome on. And finally, it would be stupid to abjure nature's greatest invention since chemistry. Thank you.